Hello, everyone. This is everything we have covered so far, combined into one server and one client. No new concepts, just the full picture running end to end. Server.py is a single fast MCP server named Recipe Helper Full Tour that consolidates every concept from sections 1 to 6. Simple tools, resources, prompts, structured return types, call tool result patterns, and async context, all in one file. Client.py connects to it via stdio client, initializes a session, then calls each tool, resource, and prompt in the same section order. No logic is shared between files. The server exposes, the client exercises. Let's open up a terminal. Let's start the stdio client and launch the server as a subprocess. The output opens with a schema dump for list underscore tools. The raw output dump, if you pay close attention, you can see output schema of null on the call tool result. Next, client runs straight through the 6 sections in order. Simple tools, resources, prompts, each printed block maps directly to a section in both files. Now that the stdio run is done, let's dive into the MCP Inspector, the official visual tool for testing and debugging MCP servers. Think of it as a postman for AI agents. Instead of writing a client just to call a tool or read a resource, you point the inspector at your server and get a UI that lets you do it all by hand. It's the fastest way to verify your server is wired up correctly before any real client touches it. We are going to connect to it directly to the same stdio server. Before launching, verify you have Node.js and npm installed. If either command fails for you, install Node. Instructions are in the description. Once Node is confirmed, launch the inspector. It's a Node.js tool, so it doesn't need your Python environment or any specific folder. This opens up the inspector UI in your browser. Let me maximize this. To connect it to the server, set the transport type as stdio and fill in the fields. First, command. This is your Python executable from a virtual environment. Next, arguments. This should point to the path on your server.py, the entry point to your MCP server. Let's hit connect. As you see, connection is now established to a local connection using the stdio transport, standard input-output. This page shows you are connected to an MCP Inspector session, the official developer tool for testing and debugging model context protocol servers. Think of it as a postman for AI agents. The history section tracks the handshake between the inspector, the client, and your server. The inspector sent an initialize request to discover what the server can do, and the server replied with its capabilities, confirming it supports prompts, resources, and tools. This is the critical first step. It's the server telling the AI, here is the menu of things I can help you with. The left section is the configuration and connection, or the control center for your MCP server. It's just how the inspector talks to your code. We have the transport setup, the server metadata setup, and the session controls, including restart and disconnect buttons. On the right side, you see the full workspace, where we will test the server's functionality and monitor the data flow. It has functional tabs for resources, prompts, tools, and many more that lets you explore server's capabilities. Currently active is resources, where you can list or query the data exposed by the server. It has history with initialize handshake and server notification, a dedicated area for asynchronous messages or logs sent from the server to the client. Let's click on list resources to access them, which fetches get underscore conversions. This has registered an event in history and notification. By clicking get conversions, you have triggered a full read operation on the server. This has registered an event in history. The main panel now shows the specific data stored at the URI. You've successfully pulled a text-based cheat sheet for cooking measurements. The server identified this as text plain, telling the inspector to render it as a standard text block rather than code or an image. We moved from discovery to retrieval. The server correctly resolved the URI and served the data through the stdio pipe. Now, let's click on resource templates and returns get underscore ingredients. Notice this has registered events in history and notification. While get underscore conversions was a simple file, get underscore ingredients is a template. Now let's click on get underscore ingredients. This has registered events in history and notification. Let's enter burger under dish and hit read resource, and the main panel now shows the result. This confirms the server is processing your input and searching its internal database in real time. We have also registered this event in history. We successfully tested the dynamic discovery capabilities of MCP. Next, by moving to prompts, we transition from simple data retrieval to using the server as a creative assistant. Let's click on list prompts, events triggered in notification and history. Let's test cooking underscore instructions. When you pass dish as omelette and skill level as beginner and hit get prompt, you see the server generated a structured prompt. You see prompts get, which indicates the inspector successfully requested the specific text string from the server based on the inputs. Next, troubleshoot underscore dish. We enter the dish as pasta and the problem as overdone. And let's hit get prompt. The JSON response shows a messages array. This is a multi-turn prompt, meaning it doesn't just give a single instruction. It sets up a conversation. Events registered in history check and notifications. We moved from resources, the what, to prompts, the how to, and the two kinds of prompts. One, returning just a string, and the other, returning a list of messages. Next, let's move on to the tools tab to see how the server can actually perform actions. Let's click on list tools, event registered in notification and history. Now, functional capabilities are unlocked. The middle pane is now populated with a list of long verbs, actions the server can take. Unlike resources, which are the data, or prompts, which are instructions, these tools allow an AI to do things. Let's invoke each of them. Double underscore servings. Our first tool takes in an integer and doubles the serving. Let's take in the input of 2 and also inspect the output schema. It clearly shows the output shape to expect. Let's run it. Result of 4 returned. Events registered in notification and history. Next, list underscore dishes. This returns a static list of strings. Let's hit run tool. Now let's run wine pairing suggester. This has a title in its name, which is used in the inspector for display, unlike the function name used when title is not provided. This takes an input string, which looks up a dictionary and returns the value if present, or sends a default value as a fallback. Let's invoke this with pancakes and the output string is returned. Next, scale_recipe. This is an MCP tool that takes a dish name, target serving count, and unit system. These have defaults and returns a confirmation string. Each parameter uses field description from Pydantic, which serves a dual purpose here. It sets default values and embeds human readable description directly into the tool's schema. When MCP exposes this tool to an LLM, those descriptions become part of the tool spec, telling the model exactly what each argument means and how to populate it correctly. Let's invoke this with pancakes and let's use the default for the other parameter. Let's hit run tool, result printed out with events registered. Next, get_nutrition. This is an MCP tool that returns nutrition data for a dish as a structured nutrition info object. Calories, proteins, carbs. It's a hard-coded stub. Only pancakes, omelette, and pasta have real values. Anything else gets zeroed out. Nutrition info is a base model, does double duty. It validates the return type and exposes a type schema to the LLM via MCP, so the model knows exactly what fields to expect back. Here, the output schema clearly describes each field. Let's invoke this with pasta and let's run the tool. It shows both structured content, schema validated, and unstructured content, raw text, both matching. Next, get cooking time. This is an MCP tool that returns prep, cook, and total time for a dish. This is a type dict. Unlike nutrition info, this uses Python's built-in type dict, no Pydantic validation, but MCP still infers the output schema from the type hint to expose structured fields to the LLM. When invoked with omelette via the MCP Inspector, let's run this. We should see structured and unstructured outputs with the necessary events in the history and notifications. Next, get_macro_ratios. This is an MCP tool that returns macronutrient percentages, carbs, protein, fat, for a dish as a plain dictionary with string and a float. Dictionary is the lightest return type yet. No Pydantic, no type dict, just a native Python dictionary. MCP still infers a schema from the type hint. Let's invoke this with pasta. Let's hit run tool. The inspector again shows structured and unstructured content, both matching. Next, get_substitute. This is an MCP tool that returns a baking substitute for an ingredient as a plain Python class with the type annotated attributes. Same stub pattern. Butter, eggs, milk have real values. Anything else returns no substitute found. The interesting split here, ingredient substitute is a plain class. No Pydantic, no type dict. So MCP introspects the type hints to build the schema. Let's invoke this with eggs. Let's hit the run tool. Structured content correctly parsed into original, substitute, ratio fields, valid against the output schema. Unstructured content is just the raw object representation. This is a key point. Without $str or wrapper, the unstructured fallback is useless. Structured content is doing all the work here. Next, get recipe note. This is an MCP tool that returns a tip for a dish as a plain Python class. But unlike ingredient substitute, recipe note has no type hints on its attribute. This is the key point. Without type hints, MCP can't introspect the class structure to build a schema. The inspector will confirm this when we invoke this with pasta. Let's hit run tool. This has generated just the raw object representation. The tool succeeds, but returns nothing useful to the LLM. Lesson: type hints aren't optional decoration. They are what MCP uses to serialize your return values. Next, check pantry. This is an MCP tool that checks a hard-coded pantry set and returns a call tool result directly, the lowest level MCP return type, giving you explicit control over the response. The key difference here, by returning call tool result manually, you can set the is error equals true to signal a tool error to the LLM without raising a Python exception. Success just omits the flag. We invoke this with salt. Let's hit run tool. This returns a plain text. Salt is available in the pantry. No structured content, just a text content block inside the result. Next, get recipe card. This returns a call tool result containing an embedded resource instead of a plain text. It wraps the recipe in a resource with a URI, MIME type, and text body. This mimics returning a file reference rather than raw data. The key distinction here: embedded resource tells the LLM this content comes from a resource, like a file or a document, not just a string, useful when you want to link content to a source URI. Let's invoke this with pasta. The inspector returns the embedded resource directly, URI, MIME type, and the recipe text. No structured, unstructured split, just the resource contents. Next, generate serving chart. Generate serving chart returns a call tool result containing image content, showing that MCP tools can return binary image data, not just text. The image is a hard-coded minimal valid PNG, which is 1 by 1 pixel base 64 encoded and passed as the data field. The serving argument isn't actually used. It's a stub demonstrating the pattern. When we invoke with 0, the MCP returns success, confirming MCP can handle image payloads. The base 64 PNG is there in the result even if the inspector doesn't render it visually. We've made a minimal change to this function such that it returns a result with generate serving chart 2. Same call tool result plus image content pattern. But now it uses pillow to actually generate a 200 by 200 blue square, saves it to an in-memory bytes IO buffer, and base 64 encodes it. The key upgrade over generate serving chart: the image is dynamically generated in memory. In a real implementation, you'd use servings to draw an actual chart here. When we invoke this with serving 0, the inspector renders the blue square directly, confirming the MCP inspector does render image content. Next, create recipe label. This generates a styled recipe label image using pillow, dark green background, white border, dish name in uppercase, and recipe label subtitle. Then it returns using fast MCP's built-in image class instead of a manual call tool result. The key difference from the previous message is returning image, which is the fast MCP shorthand. It handles the base 64 encoding and image content wrapping for you, keeping the code cleaner. Let's invoke this with pasta. The inspector renders the label directly, a green rectangle with pasta and recipe label text, confirming FastMCP's image class produces the same render output as the manual call tool result approach. Next, get dish info. This returns a call tool result with two distinct payloads: the content visible to the LLM and underscore meta, client only metadata, never passed to the model. The key concept: underscore meta is a sidecar for the client, logging, UI hints, provenance tracking, without polluting what the LLM sees. The model only gets the text description. Let's invoke this with pancakes and run the tool. The inspector shows this split clearly: meta, category, difficulty, and source. And the tool result, just the text, nothing else. Next, clear added dishes. This removes any dishes added beyond the three base ones from the shared recipes dictionary, then returns an empty content list as a completion signal response. The key point is the content empty is a valid MCP response. Let's run this. This tells the LLM that the action succeeded with nothing to report, appropriate for destructive write operations where there's no meaningful return value. The inspector has confirmed this. Tool result success with no content rendered below. Next, get validated macros. This is the most complete response pattern yet. It explicitly populates all three output channels in one call tool result. Structured content, machine readable dictionary validated against macro summary via annotated content, human readable text for the LLM underscore meta, client only sidecar, not visible to the model. Let's invoke with pasta as the dish and let's hit run. The inspector confirms all three when invoked with pasta: structured content, meta, and unstructured content. Next, generate shopping list. This is an async MCP tool that takes a list of dishes, deduplicates all their ingredients, and returns a sorted shopping list. It uses context to emit live progress and log messages during execution. The context parameter is the key here. It gives the tool a channel to send structured notifications back to the client mid-execution. Info, debug, warning, log levels visible in the notification and history panel. Report underscore progress emits progress ticks the client can display. Error signals a terminal error. Let's invoke this. The input is a list. When I hit run tool, you would see a lot of action in history and server notifications. Several notifications were registered. Most of these notifications were a part of that execution. If you open each one of these, building shopping list, processing pancakes, progress 25%, another notification, 50% progress, 75% progress, another info log, processing all four, processing the last item, and the final warning. Several events were fired per dish, and a warning for soup, not in recipes. The output, structured and unstructured, which is the final deduplicated shopping list across all known dishes. Next, add underscore dish. This adds a new dish and its ingredients to the shared recipes dictionary. Then fires context.send resource list changed, an MCP notification telling connected clients that the resource list has changed. This is the critical line, and this is what makes the new recipe dish URI dynamically discoverable without restarting the server. The resource list is open world. Clients can subscribe and react to this notification. Let's invoke with dish of pie and ingredients of apples. Let's hit run tool. The output is generated as expected. The natural next step is to check the resources tab. Let's hit get underscore ingredients, and under the dish, Let's hit pie. Let's hit read resource. And you see the ingredients for pie is apples. That is what we had provided for add underscore dish tool, proving the send resource list change notification work. Finally, the MCP Inspector is a visual debugging layer that sits between you and your server, letting you invoke tools, inspect every request response, and observe server notifications in real time without writing a single line of client code. Across all tools we explored, it consistently exposed three things: what the LLM sees, what the client sees, and where things break. It's not just a convenience tool, it's the fastest way to verify your MCP server behaves exactly as intended before connecting to a real client. Now, let's connect a streamable HTTP server to the MCP inspector. Let's stop the server. Let's go to the server code and comment out the transport of stdio with streamable HTTP. Now, let's start the streamable HTTP server. The streamable HTTP server is fired up. Let's open another PowerShell. Let's start the MCP inspector again. Next, let's change the transport as streamable HTTP. This is the default URL. Let's hit connect and everything works as expected. We have just changed the transport type, but all the other operations are exactly the same. We've come a long way. Now, the only thing pending is connecting our server to Claude Desktop. We need to make sure that the server is stdio and we're going to launch via a local subprocess. Let's open Claude. Then let's open Claude config.json. Go to settings, developer, edit config, open this in your text editor. I have already prepared the new config. Let me bring here. And now inside the MCP servers object, I'll be adding the new MCP server, giving it an arbitrary name, in our case, full tour server with command and arguments. Command points to your Python executable. So if we go into our project and if you go into the environment, scripts in case of Windows and python.exe, this is what is copied. And then the server path for this file, make sure your transport is stdio. So yes, command is the Python executable and arguments is your server path. Let's remove this. Let's save this. Let's go back to Claude settings. Let's open connectors. We don't see it yet. Let me close and reopen Claude. I have a task manager open. So I'm going to end this task. Now I'm going to reopen Claude connector. And that's the server we've specified. Let's invoke the server. And yes, we can invoke our server through Claude Desktop.